Hello everyone, my name is Ethan Walsh. I'm here to talk about the applications of point defects. So first off, vacancy defects are basically when there's a missing atom at a certain crystal lattice position. So basically where there should be an atom, there's one missing. And they can occur for any crystalline solid that is above absolute zero temperature. And there are many ways for vacancy defects to occur, but one of the main ones is when the solid is heated and then slowly cooled, as this causes the vacancies to form as a result of thermal vibrations and rearrangements of the atoms in the crystalline lattice. So here's my model for it. As you can see, there's a crystalline lattice for the material silicon, but it doesn't really matter. As you can see, when I click away, you can see that some of those atoms are now gone, or vacant, as you might say. Anyway, that's just an idea. Anyway, let's talk about some effects and applications. So one effect of vacancies in a crystalline solid is vacancies defects can affect the electrical properties of materials, such as their conductivity. The presence of vacancies can introduce charge carriers or alter the band structure of the material, influencing its electrical and behavior performance. And then another one is vacancy defects can also affect the thermal properties of materials, such as thermal conductivity, specific heat, coefficient of expansion, and basically the reason for that is the presence of vacancies can disrupt the phonon transport, which affects the material's ability to conduct heat and store and release energy. And then just a couple of applications are optical applications, and then the uses for these vacancies could be for radiation shielding or even energy storage. So very useful things. Next, we've got interstitial defects, which are basically when foreign atoms or ions are occupying interstitial sites, or usually like in between where the normal crystalline lattice atoms would occur. And they can occur, one of the main ways they can occur is through diffusion. So here's my model. I kind of had to put a red circle around it as it was a little hard to see, but as you can see, it all looks like a nice pattern, and then there's one that's just kind of out of place. This is also silicon, by the way. So one application of this could be semiconductor materials, which are used by silicon, and interstitial defects can be introduced intentionally during the fabrication process to create dopant atoms or ions that are interstitially trapped in the lattice. This is known as doping and is a key process in the production of semiconductor devices, as it is key process for the production of conductor devices such as transistors, diodes, and integrated circuits. So that's one useful application. And then another thing is it can be used for radiation detecting. So basically, interstitial defects can be used when high energy particles such as alpha particles, beta particles, or gamma rays pass through a material with these defects. And they can basically create these defects from their lattice positions. And then last but not least, we've got substitutional defects, which are involves the replacing of an atom in the lattice with another atom. This can be caused from natural impurities with solids, as well as heat treatment processes for things like alloys and such. So my model shows, again, the silicon crystalline structure with phosphorus dispersed throughout. And then some applications for this are it can basically alter the physical properties of the material, which can lead to a lot of uses. Alloys are a really big one. A specific alloy for that is brass, which is made of copper and zinc. And this alloy, the mixture of these materials, allow it to be a good corrosion resistance, and that means it makes it suitable for various environments, including marine, industrial, and outdoor applications. So there are definitely a lot of uses for changing the properties using substitutional defects, as it can change like the hardness, the strength, or even the conductivity for whatever the job might be for that material. All right, thank you for watching.